87 kilometers beneath the Tyrrhenian Sea, something connects two of Europe's most active volcanoes. And researchers are now arguing about what it means. Not a metaphorical connection, not a shared tectonic neighborhood, a physical pathway, a conduit threading through the seafloor crust, potentially allowing magma, heat and pressure to move between Mount Etna on Sicily's eastern coast and Stromboli in the Aeolian Islands to the north. And if that pathway is real, if it behaves the way some scientists now fear it might, then the 4 million people living across Sicily and Calabria are sitting above a geological system that nobody has fully mapped until now. That's the finding that's quietly reshaping conversations inside INGV. The Istituto Nazionale di Geofisica e Vulcanologia, and across volcanology departments from Catania to Potsdam. It's not a press conference discovery. It came out of years of seismic tomography data, cross-referenced with magnetotelluric imaging surveys, interpreted by researchers who kept asking why two volcanoes so different in character kept doing strange coordinated things. Why does Stromboli sometimes intensify its activity in the weeks after a major Etna paroxysm? Why does the geochemical signature of gases at both systems occasionally mirror each other, despite a nearly 90-kilometer gap of open water? These questions weren't accidents. They were clues. The central question this research is forcing the scientific community to confront is genuinely uncomfortable. Can two volcanoes be linked at depth in a way that produces what researchers call sympathetic behavior, where activity at one site could, under certain conditions, trigger or amplify activity at the other? And if that answer is yes, even partially, even conditionally, what does that mean for emergency planning, for evacuation modeling, for the millions of people who live in the blast shadow of either system? We don't have a final answer yet, but the data is pointing somewhere specific. And that direction is worth understanding clearly. To understand why this discovery matters so much, you need to stand back and look at the geography of this part of the Mediterranean. Really look at it, because it's unlike almost anywhere else on the planet where volcanic activity is concentrated. The Tyrrhenian Sea sits like a basin cupped between the Italian peninsula to the east, Sardinia and Corsica to the west, and Sicily to the south. It's not a deep oceanic plate in the traditional sense. It's a back arc basin, a region of thinned, stretched crust that formed as the Calabrian arc subduction zone retreated southward over millions of years. That process left the seafloor here unusually thin in places, punctuated by seamounts and volcanic structures that break the surface in the form of the Aeolian Islands. The Aeolian archipelago is a chain of 7 volcanic islands scattered across the southern Tyrrhenian. Stromboli sits at the northeastern tip of that chain. Volcano anchors the southern end. Lipari, the largest island and the one most densely settled, sits between them. Stromboli is the one volcanologists watch most obsessively. It's been erupting almost continuously for at least 2,000 years, earning its title as the lighthouse of the Mediterranean from ancient sailors who used its persistent glow to navigate at night. Today, it rises roughly 924 meters above sea level, though its volcanic edifice extends nearly 3 kilometers below the waterline before it meets the seafloor. It's been active at some level for so long that its style of eruption, frequent, rhythmic, moderately explosive bursts from a summit crater, is named after it. Strombolian activity is now a formal volcanological classification. Then there's Etna. Mount Etna is a different beast entirely. It stands 3,157 meters above sea level on Sicily's northeastern flank, close enough to Catania, a city of nearly 400,000 people, that you can see it from the waterfront on a clear day. Etna is the largest active volcano in Europe by volume, and it's been in near continuous eruption for at least 500,000 years. Its character alternates between effusive lava flows that move slowly enough for communities to retreat, and violent paroxysmal episodes that send ash columns 30 to 40 kilometers into the stratosphere, shutting down Catania, Fontanarossa Airport, and dusting the city in grey powder. Messina, about 30 kilometers northeast of Etna's summit, sits in its shadow. Reggio Calabria, across the Strait of Messina on the Italian mainland, is barely 50 kilometers from the volcano's base. The scale here is worth sitting with. In the Pacific Northwest, The Cascadia subduction zone is feared because it sits beneath a coastline of roughly 10 million people. In Hawaii, hotspot volcanism is monitored intensively because communities have expanded into lava flow corridors that didn't exist on hazard maps a generation ago. The southern Tyrrhenian is similar. Population centers here aren't adjacent to volcanic systems. They're embedded within them. Catania was partially destroyed in 1669. Messina was devastated by an earthquake in 1908. Stromboli's 2002 tsunami reached the shoreline of Calabria. These aren't hypothetical risks. They're historical facts. And now, researchers are suggesting that Etna and Stromboli may not be two separate volcanic risks. They may be components of a single, partially connected system. So how does a pathway 87 kilometers long get proposed as a geological reality? And what exactly does that pathway look like beneath the seafloor? Let's start with the tectonic setting, because it explains why this region is so volcanically complicated to begin with. The African plate is diving beneath the Eurasian plate in this part of the Mediterranean, but not in a clean, uniform way. The subduction geometry of the Calabrian arc, the curved thrust fault system, that arcs beneath southern Italy and Sicily, is among the most complex in the world. The African plate's descent here is fragmented, its slab torn and retreating. That retreating slab is what opened the Tyrrhenian back arc basin over the past 8 to 10 million years, and it's what continues to drive both compression along the Calabrian arc and extension within the basin itself. The result is a crust that behaves differently in different places. Thick and rigid under parts of Sicily, thin and hot under the Tyrrhenian, fractured and faulted almost everywhere in between. Etna's magmatic system taps into this complexity. Its magmas are fed by a deep source, possibly influenced by the edge of the subducting African slab, possibly by partial melting of the mantle wedge above it, possibly by both. The INGV Catania Observatory, which monitors Etna more closely than any other institution on Earth, has been tracking changes in the volcano's plumbing system for decades, using everything from seismic arrays to satellite-based ground deformation measurements. What they've found is that Etna's magma storage zone isn't a single magma chamber in the Hollywood sense, a glowing lake of liquid rock just waiting to burst. It's a network of interconnected storage zones at different depths, connected by pathways through the crust. Stromboli's system is similarly complex, monitored intensively by INGV's Osservatorio Vesuviano in Naples, INGV-OV, which also covers the Aeolian Islands. Stromboli's magma is thought to rise along a relatively direct pathway from a deep source, but that source's relationship to the broader tectonic setting of the Tyrrhenian back arc basin has always been somewhat unclear. What the recent research, drawing on seismic tomography surveys conducted partly in collaboration with GFZ Potsdam, Germany's National Center for Geosciences, is suggesting is that both systems may share a portion of their deep plumbing. Seismic tomography works something like a medical CT scan, but instead of X-rays, it uses seismic waves generated by earthquakes. When those waves pass through hot, partially molten rock, they slow down. When they pass through cold, rigid rock, they speed up. By recording those wave arrivals at hundreds of seismometers and running sophisticated inversion algorithms, researchers produce three-dimensional images of the crust and upper mantle, seeing structures no drill could ever reach. What the tomographic images beneath the southern Tyrrhenian are showing, and this is where the science gets genuinely surprising, is a low-velocity anomaly, a zone of slower seismic waves that extends from beneath Etna's deep root system towards the northeast, connecting, at depth, with a similar anomaly beneath the Aeolian Islands. This anomalous zone is hotter than the surrounding rock. It may contain small fractions of partial melt, and it threads through the crust at depths between roughly 20 and 40 kilometers, over a horizontal distance of approximately 87 kilometers. Magnetotelluric imaging, which maps the electrical conductivity of the crust using natural variations in Earth's electromagnetic field, adds another layer of evidence. Partially molten rock conducts electricity better than solid, dry crust. Surveys analyzed by teams at the University of Catania show elevated conductivity along a corridor that broadly matches the tomographic anomaly. Two independent methods, one shared picture. Now, there's an important distinction scientists are careful to make. There's a difference between a thermal pathway and an active magma conduit. A dike is a sheet-like intrusion cutting across existing rock. A fast, forceful connection. A sill is a horizontal intrusion spreading along bedding planes. Slower, less direct. A thermal anomaly might simply be hot rock conducting heat efficiently without moving significant volumes of magma. Think of it as the difference between two rooms sharing. A warm wall and two rooms connected by an open doorway. The wall heats both rooms. Only the doorway allows something to pass through. The disagreement within the research community right now is precisely about which of those scenarios the data supports. INGV researchers in Catania tend toward cautious interpretation. The anomaly is real, the connection is real, but whether it constitutes an active magmatic pathway capable of transmitting significant pressure or melt between the two systems remains unconfirmed. Researchers at GFZ Potsdam, who contributed to the tomographic analysis, have been somewhat more willing to entertain the hypothesis that stress transfer, not necessarily magma transport, but shifts in pressure within the connected system, could be operating between Etna and Stromboli right now. And stress transfer between volcanic systems, even without direct magma movement, is a recognized mechanism for what volcanologists call sympathetic eruptions. That concept of stress transfer is critical. It's not fringe science. It's been documented at volcanic systems in Iceland, Kamchatka, and across Central America's volcanic arc. When one volcanic system undergoes a significant pressurization event, the stress changes in the surrounding crust can push nearby systems closer to, or further from, their own eruption thresholds. The question for the Tyrrhenian system is whether the 87 kilometers of potentially connected pathway is short enough and hot enough that stress changes at Etna could be felt by Stromboli, or vice versa, on timescales of weeks rather than centuries. Researchers can't answer that definitively yet. The data is compelling. The physical mechanism is plausible, but the confirmation requires years of additional monitoring and possibly the kind of deep-sea seismic instrumentation that simply doesn't yet exist in the gap between Sicily and the Aeolian Islands. Here's where the historical record becomes genuinely important and genuinely unsettling. Etna has been erupting persistently throughout recorded history. The ancient Greeks and Romans wrote about its fire. Medieval Sicilians built their churches from its lava. But the eruption that changed everything for the communities around Etna happened in March of 1669, and it remains one of the most catastrophic volcanic events in European history. Over the course of 4 months, Etna produced a lava flow that traveled roughly 15 kilometers from its southern flank, burying more than a dozen villages and reaching the walls of Catania itself. The flow destroyed a significant portion of the city's western districts. Contemporary accounts describe residents watching the advancing lava front from their rooftops, unsure whether the city walls would hold. And in many places, they didn't. Historical estimates suggest the eruption killed somewhere between 10,000 and 20,000 people. Catania today is a city of nearly 400,000. The lava plains that surround it on the west and southwest are the product of eruptions exactly like 1669. Etna's paroxysmal episodes in the modern era are better understood, but no less dramatic. Between 2011 and 2023, Etna produced more than 70 distinct paroxysmal episodes, sequences of intense explosive activity from its summit craters, generating ash columns that repeatedly disrupted air traffic across the central Mediterranean. Each of these episodes, as INGV Catania monitoring data documents, is preceded by ground deformation detectable by GPS networks, increased seismicity in the volcano's conduit system, and rising SO2 flux from its summit vents. The pattern is recognizable. The timing is not perfectly predictable. Stromboli's history has a different texture. Less catastrophic in most years, but capable of sudden violence. The volcano's baseline Strombolian activity is almost reassuring in its regularity. Small explosions every 15 to 20 minutes. Lava fragments thrown 50 to 200 meters into the air. A persistent glow visible from miles away. It's been doing this with brief interruptions for centuries. That's what earned it its navigational reputation. But then there are the anomalous events, the ones that don't fit the pattern. In 2019, Stromboli produced two major explosions in July and August, sending pyroclastic material down its Sierra del Fuoco, generating small tsunamis and killing one hiker. But it was the 2002-2003 eruption sequence that demonstrated what Stromboli is truly capable of when it steps outside its normal behavior. Beginning on December 28, 2002, a major effusive eruption opened on Stromboli's flanks. Within hours, two submarine landslides, one on the northern flank, one on the southern, failed catastrophically under the weight of the new lava, loading the volcano's unstable slopes. Those landslides generated tsunami waves. The largest waves measured approximately 10 meters in height as they struck the island's shoreline, destroying portions of the village of Stromboli and the settlement at Ginostra. Waves were recorded across the Tyrrhenian as far as the coasts of mainland Italy and Sicily. Several hundred people were evacuated. By extraordinary fortune, the event occurred during the winter low season, when the island's tourist population was minimal. Imagine that scenario playing out in August, when Stromboli's small permanent population of roughly 500 is swelled by thousands of tourists. The casualty arithmetic changes dramatically. It was during the monitoring of the 2002 eruption that something interesting caught the attention of an INGV technician working the night shift at a monitoring station in Catania. Reviewing seismic waveform data from the regional network, she noticed that the onset of the Stromboli crisis had been preceded, by approximately 11 days, by an unusually intense episode of deep seismicity beneath Etna's flank, at depths consistent with activity in the lower crustal portion of its magmatic system. She flagged the correlation in an internal report. It wasn't published. It wasn't definitive. It was the kind of observation that gets filed away, noted, but not acted upon, because the scientific bar for claiming a connection between events 87 kilometers apart is extraordinarily high. But that file didn't stay closed. 2 decades later, the tomographic and magnetotelluric surveys are forcing exactly that correlation back onto the table. Then versus now. In 2002, researchers had regional seismic networks, limited GPS coverage, and no systematic imaging of the deep crust beneath the Tyrrhenian seafloor. In 2025 and 2026, they have broadband seismic arrays, continuous satellite radar interferometry, dense GPS networks on both Sicily and the Aeolian Islands, and the first high-resolution geophysical surveys of the sub-seafloor pathway between these two systems. The data quality has transformed, and with it, the questions that can be asked. What does the monitoring picture look like right now, and what are its limitations? The INGV seismic network across Sicily and the Aeolian Islands is one of the densest volcanic monitoring arrays in Europe. INGV Catania operates dozens of permanent broadband seismometers on Etna's flanks, capable of detecting events as small as magnitude 0.1 within the edifice. A parallel network run by INGV-OV covers the Aeolian Islands, with instruments on Stromboli, Vulcano, and Lipari, linked in near real time to servers in Naples. Those networks share data through Italy's national INGV backbone and increasingly through the EU's EPOS, the European Plate Observing System, which aggregates geophysical monitoring data from across the continent into standardized, interoperable formats that research teams from Catania to Potsdam can access simultaneously. GPS deformation networks on both volcanoes continuously track ground movement to fractions of a millimeter per day. When Etna's magmatic system pressurizes, its flanks bulge in patterns GPS can detect weeks before visible eruption begins. Stromboli's GPS network tracks both the slow gravitational spreading of the edifice and the sharper inflation signals that precede significant eruptive episodes. Gas chemistry monitoring adds another dimension. Permanent multi-gas sensors on both volcanoes measure CO2, SO2, and hydrogen sulfide concentrations in real time. Changes in the CO2 to SO2 ratio in volcanic gases are sensitive indicators of magma rising from greater depth. Because CO2 exsolves from melt at higher pressures than SO2, changes in that ratio can signal whether fresh, deep magma is entering the shallow storage zone. INGV researchers have published multiple studies showing that shifts in Etna's gas chemistry have preceded its paroxysmal episodes by days to weeks. Whether similar gas signals might telegraph changes in the proposed deep connecting pathway between Etna and Stromboli is currently unknown, because the sensors measuring them sit on the surface, far from the deep crust where any connection would operate. Tilt meters, instruments that measure tiny changes in the angle of the ground surface, provide yet another monitoring layer. Both Etna and Stromboli carry networks of electronic tilt meters that can detect inflationary or deflationary signals at the scale of microradians. During Stromboli's paroxysmal episodes, tilt meters on the island often register sharp deflation signals as magma evacuates from shallow reservoirs during explosive bursts. Here's the monitoring gap that concerns researchers most, and the director of INGV Catania has been explicit about this in recent statements to the Italian scientific press. There is almost no real-time seismic or deformation monitoring of the seafloor corridor between Sicily and the Aeolian Islands. The proposed 87-kilometer pathway lies almost entirely beneath open water, at depths ranging from several hundred to over 3,000 meters below the Tyrrhenian surface. Ocean bottom seismometers have been deployed here during specific research campaigns, but no permanent, continuous network exists along this corridor. The very portion of the system that might transmit stress or melt between the two volcanic systems is, from a real-time monitoring perspective, essentially dark. Scientists can see what Etna is doing. They can see what Stromboli is doing. What happens between them, at depth beneath the Tyrrhenian seafloor, is still largely invisible. INGV-OV has formally identified this gap in published assessments and is seeking funding through EU research programs to establish a more permanent deep-sea monitoring presence in the Tyrrhenian. But that infrastructure doesn't exist today, and in the meantime, the two systems continue their activity with that critical middle section unobserved. What happens if the connection is real, and what does the conditional modeling suggest about risk? Researchers working with dynamic stress modeling software, the kind of computational fluid dynamics and elastic stress codes used by teams at GFZ Potsdam and at the University of Catania's volcanology group, have run scenarios to explore what might happen if the proposed pathway is not just a thermal anomaly, but an active dike system capable of transmitting pressure changes. These are models, not predictions. They're tools for understanding the range of possible outcomes, not statements about what will happen. In the conditional scenario, where the pathway transmits significant stress, a major pressurization event at Etna, the kind of deep magmatic intrusion that precedes its largest paroxysmal episodes, could potentially shift stress conditions at the Stromboli end of the pathway within days to weeks. The magnitude of that stress transfer would depend on factors researchers don't, yet have good constraints on: the exact geometry of the connecting zone, its temperature, the degree of partial melt it contains, whether it includes fluid-saturated fracture zones that conduct pressure efficiently. If those conditions favor transmission, models suggest that Stromboli's already elevated activity could intensify in the weeks following a major Etna event. Not certainly, not automatically, but potentially. And here's where the tsunami risk re-enters the picture in a way that demands serious attention. Stromboli's 2002 event showed that the volcano is capable of generating Tyrrhenian-wide tsunami waves when its flanks fail. Those 2002 waves, estimated at approximately 10 meters as they struck the island, were generated by submarine landslides triggered by effusive eruption loading the Sciara del Fuoco. A larger or more sudden flank failure, driven by a more energetic eruption, could theoretically generate waves significantly larger. The Tyrrhenian Sea is essentially a closed basin. Waves generated near Stromboli would reach the Calabrian coast in minutes. They'd arrive at the Sicilian coast, including Messina and nearby communities, within 30 minutes. Evacuation of low-lying coastal areas within that window is possible, but only if warning systems are functioning, only if the public knows what to do, and only if the triggering event is detected quickly enough. Meanwhile, any significant increase in volcanic activity at either Etna or Stromboli carries consequences for air traffic across the entire central Mediterranean. Etna's ash plumes have forced closure of Catania Fontanarossa Airport, one of Sicily's primary international gateways, on multiple occasions. Palermo's Falcone Borsellino Airport has also been affected by Etna's more dispersed ash clouds. Stromboli's emissions, while usually lower in volume, have occasionally affected routing across the Tyrrhenian. If both systems were to intensify simultaneously, a scenario that remains conditional but is no longer dismissible as impossible, the combined disruption to airspace over the central Mediterranean could be significant. Airlines routing between Northern Europe and the Eastern Mediterranean, North Africa, and the Middle East regularly transit this airspace. The economic ripple effects of extended closures at major southern Italian airports would be felt across the continent. None of this is inevitable. That word doesn't belong in conversations about volcanic systems that are inherently probabilistic and deeply dependent on conditions that science can partially, but never completely constrain. What researchers are saying is that the probability of sympathetic behavior, of one system influencing the other through the newly identified pathway, is higher than previously modeled because the previous models assumed independence that may not actually exist. What do we take from all of this? Geology moves on its own schedule, indifferent to ours. The Calabrian arc has been subducting for millions of years. The magmatic systems beneath Etna and Stromboli have been operating for hundreds of thousands of years. The 87-kilometer pathway being described by seismic tomography and magnetotelluric imaging wasn't. Created recently, it's a feature of the deep crust that researchers simply didn't have the tools to see until now. The discovery isn't alarming, because something new is happening underground. It's significant because it's changing what we know about what has always been happening underground. And that distinction matters enormously for the 4 million people living in the path of these systems. In Catania, in Messina, in Reggio Calabria, in the small coastal towns of Calabria, in the fishing villages on the flanks of the Aeolian Islands. They deserve to have their risk understood as clearly as the science allows. They deserve monitoring systems that don't have a dark zone at the most critical point. They deserve emergency planning that accounts for the possibility, conditional, uncertain, but real, that Etna and Stromboli might not behave as independent events. Scientists can't tell you when the next major eruption will happen. No honest researcher would claim otherwise. What they can tell you is that the system is more interconnected than the hazard maps currently reflect, and that closing that gap between what monitoring covers and what the geology actually does is urgent, important work. If this deep structural connection between European volcanic systems concerns you, and it should, not because catastrophe is certain, but because understanding it properly requires resources and attention that aren't yet fully committed, then the next question worth asking is about what's happening beneath the Italian mainland itself. Because roughly 150 kilometers northwest of Etna, beneath the sprawling, restless volcanic field of Campi Flegrei near Naples, 3 million people are living above a caldera system that has been slowly but measurably inflating for decades. And the latest ground deformation data from INGVOV raises questions that make the Etna Stromboli pathway look, by comparison, almost simple. That story is coming. In the meantime, if this kind of deep geological investigation is something you want to follow, the science that most people don't see because it happens at 40 kilometers depth beneath open water, this is the place to stay. The researchers are watching. The instruments are running. And the Tyrrhenian Sea is keeping its own record in seismic waves and magnetic fields. And the slow, patient chemistry of magma, whether we're reading it carefully or not.